Greetings. In previous chapters, we saw how multiple processes or threads can share resources, and how these processes or threads can utilize mutexes or semaphores or monitors to keep these resources and processes safe from each other. In this section, we're going to study deadlocks, or a problem when a set of processes hold resources while another set of processes want resources, and a vicious cycle occurs. In particular, we're going to look at resource allocation graphs so that we can model resources and processes and possible deadlock. First, let me introduce the resource system model. Resources are things that are shared by multiple processes. For instance, a synchronized section in Java, or a section guarded critical section guarded by a mutex in C++. They can also be things like memory space or I/O devices if we want to look more generally. Each of these resource types can have multiple instances. The last part of our model will be processes, and these processes request instances of these different resources. When a process requests an instance, it holds that instance, it uses the instance, and it releases the instance. There's a few factors about the instance that are important, or the usage of that instance by the process. First, only one process at a time can use an instance of a resource. Second, hold and wait. A process holding a resource and waiting to acquire other resources held by other processes will continue holding that resource. It cannot drop a resource that it holds. And then finally, if a process holds a resource, it cannot be preempted by another process. It must agree to release the resource itself. Let's look at a little more detail at the model. The model consists of a set of vertices and edges. The vertices are of two types. There are processes and there are resources. Generally, we model processes with circles and resources with squares. In this case, we have two processes and two resources below. Edges are of two types, a request edge and an assignment edge. A request edge goes from a process to a resource. This says a process wants this resource. Imagine grabbing a mutex before entering a critical section. And then an assignment edge. This points from the resource back to the process, and it says that the process itself holds that resource. It will hold the resource until it's done, and then the edge will go away. This example should make it clear. At the top, we have a process. The next line down shows a resource that has 4 instances. That process, PI, requests an instance of the resource, RJ. You can see in the 4th line down, that process PI is holding a single instance of the resource, RJ. And then finally, the instance of the resource is released by the process, and we see no edge between the resource and the process. Here's an example of a situation where we have 3 processes and 4 resources. Resource 1 and 3 each have 1 instance. Resource 2 has 2 instances, and resource 4 has 3 instances. Let's look a little more deeply. Notice process 1 wants to get an instance of resource 1, but it can't because it's being held by process 2. Process 2 is waiting for an instance of resource 3. It can't grab that because it's held by process 3. Now, if process 3 would release its instance of resource 3, which it can because it's not waiting on any other instance of a resource, then process 2 would get assigned that instance and use it. It would release it, and process 2 could then go ahead and release R1, which process 1 could get to it. So notice we are not in deadlock yet. However, could deadlock occur? Is it possible? Take a look for a second and pause this video and see if you could imagine what could happen to cause deadlock in the current situation. Welcome back. Take a look what would happen if process 3 requested an instance of resource 2. It won't be able to get that resource because both instances are held at this point, one by process 1 and one by process 2. Process 1 can't make forward progress because it needs resource 1. Process 2 can't make forward progress, it needs resource 3. And unfortunately, process 3 is blocked as well. And so we see this cycle, P3 to R2, P1 to R1, to P2 to R3 and back to P3, whereby we have deadlock. There's another cycle as well. P2 can't make forward progress because it needs resource 3, but that's held by P3, which can't make forward progress because it needs resource 2, and that's held by P2, unfortunately. So we have another cycle whereby we can't make forward progress. Let's take a look at another example. Here we have two resources, each with 2 instances, and we have 4 processes. Is there a deadlock here? Take a second and look. You may see that there's a cycle, including P3 and P4, P3 and P1, but that does not necessarily mean there's deadlock. Let's assume that P2 finishes with its resource or its instance of that top resource. That frees up an instance so that P1 can now get that resource. It will release that resource, and then it can release the resource that P4 requires as well as P3. And so notice here we have a deadlock cycle, but not necessarily a deadlock. So a couple things to note with these types of graph. First, if there is not a cycle, then there is no deadlock. If there is a cycle, there may be a deadlock. If there is a cycle and all of the resources within that cycle only has one instance, then there is certainly a deadlock. So to repeat, no cycle, no deadlock. If each resource has one instance, then a cycle means a deadlock. If some of the resources within the cycle have more than one instance, then maybe not a deadlock. Let's summarize. For a deadlock to occur, we need to have 4 things happening simultaneously. 1, the resources that we're sharing require mutual exclusion. That is, only one process at a time can use the resource. Number 2, a process can be holding a resource, and it can be requesting another resource without dropping that first resource. Number 3, when a process holds a resource, it only itself can release that resource. It cannot be preempted by another process or an operating system to release the resource. And finally, there's a circular wait whereby there's a set of processes such that process 0 is waiting for a resource which is held by process 1. Process 1 is waiting for a resource which is held by process 2, all the way around until process N is waiting for a resource held by process 0. If these 4 conditions are held simultaneously, then a deadlock has occurred. We can use a resource allocation graph to help us think about and model these situations.